This is the steamboat problem. I know there was some trouble with this. Word problems are always tricky, and when you have to set up your own model, that can be a little bit complicated, and then there are questions to answer based on that. But overall, it was pretty good. I do think I saw some that was just time struggle, running out of time on this one. But in case there was anything that wasn't just getting a little rushed at the end, I wanted to make sure that you had this video so that you could look back through and make sure you understand everything. Okay, so we have a water wheel on a riverboat, paddle wheel, I guess it's called, and we're imagining that there's some point P going around the outside. So this is like visualizing our point moving around the unit circle, but it's not a unit circle, it's a little bigger. We know that it has a diameter of 18 feet, which means radius is 9 feet. So I'm just going to mark that off. And we also know that at t equals 4 seconds, we're right at the top. So when t equals 4, we're at d is 16 feet. Okay, and the entire diameter is 18 feet, so that means that the bottom 2 feet of this does go underwater. So d is the distance from the surface up to the top of the wheel. Okay, so we want to write our equation. Oh, one more thing that I didn't write down. It makes a complete revolution in 10 seconds. Okay, so it helps me a lot if I actually graph this out as a sine wave. So I know that after 4 seconds, so let's go 2, 4, we were at our maximum height of 16. So we'll just put that near the top here. And then we know after 10 seconds, we'll be back up there. So 4, 6, 8, 10, 12, 14. So that's one full period has to happen in that time frame. Exactly in the middle, so at 9 seconds, it has to be at the bottom. So 4, 6, 8, 10, 12. Okay, so right here at 9 seconds, we have to hit the bottom, which is at -2. 2 feet below the surface. And then we can even split it up more and get equilibrium, but I don't know that we need to. I think this is getting pretty good. So there's one full period. We could go back the other way as well. Back at -1, we'd be at the bottom again. That's not necessarily meaningful for this problem. Sorry, a little lopsided looking. This was 416, but it might be helpful when we're graphing, so just giving myself a little extra room there. Okay, so we need to have a period equal to 10 seconds, which means our b value, the thing that'll hook to our time variable, has to be 2 pi over our period, or pi over 5, that'll reduce to. So I'm going to say I want a pi over 5, and then t, and then I'll have room for phase shift and equilibrium, and then I'll have to pick sine or cosine as well. Equilibrium, so this goes from -2 to 16, so that's a total of 18, which means the middle is 9 feet above the bottom, and that 9 is also, you could have gotten that straight from your radius. So -2 plus 9 is 7, and just to check myself, 7 plus 9 is 16. So it looks like the middle, the vertical center, is at 7. Y equals 7 or d equals 7, whatever you want. So that gets added on to my function. And then out in front of my function, I need that amplitude. How far does it go up or down? That's the 9 that I just labeled. Okay, so either now or if you have already, that's great. We need to decide if we're going to use a sine or a cosine. And I usually decide that entirely based on, do I know a max or a min that I'm going to try and line up with, or do I know an equilibrium point that I'm going to try and line up with? I haven't bothered to find equilibrium, so I'm going to choose a cosine. And I'm going to shift it over so that the maximum of cosine, which usually happens right at your y-intercept, will instead happen at t equals 4. Which means I'm shifting right 4. You could also line up, say, with this minimum right here. And to do that, I would say flip your cosine upside down And so put a -9 out in front, and then shift to the left one, so +1. That would be another correct equation. And of course, you could use sine correctly as long as you shift it so that one of these equilibrium points match up. You'd be in great shape. Okay, so that's my equation. How far above the surface was the point when Mark's stopwatch reads 17 seconds? This is a technology question. I don't need to see any work for this. So I'm going to jump over to Desmos just to check it. And I've already got this typed in, so you don't have to watch me do that. But I didn't play with my window yet. This one isn't too far off. I could just kind of scooch it down a little. But remember also, you can go in here and adjust. Let's see. Yeah, that's actually pretty good. But you can always go in here and adjust your Xmin, Xmax, Ymin, Ymax to make these fit. They're definitely not always just going to fit nicely in a window that we start with in Desmos. Okay, so what was our question? Our question was stopwatch reads 17 seconds. So I'm just going to go in here and type in T is 17. You can try to drag along. Well, how did that break it? Oh, because it doesn't like my variable. I'm just going to say X is 17. So Desmos, they recently added that you can put other variables here, but still, if you're just putting in an equals like that, what it's doing is actually saying this T has to be 17. So stick with X and Y if in doubt. And there's that 17-second mark, and without having to work very hard, I see that it's 4.219, so I'm going to say about 4.22. That should be feet, I believe. Okay, part C. This is the one we're going to need some work for. So let's go ahead and actually crunch through this. You can absolutely check with your graph if you're using Desmos or another calculator, but I specified here because I want to see that algebraic solve. So we want to know what's the first time when we hit the water surface. So I'm going to take my equation and set it equal to 0. 0 represents the water surface here, height of 0. And for steps, I'll start by subtracting 7 from both sides. So I get 7 equals my 9 cosine pi over 5 t minus 4. You're welcome to distribute that pi over 5 through if you'd like to. It ends up being the same amount of steps for solving. So whether you keep it in parentheses or don't doesn't really matter. You can make that decision. Okay, divide by 9. And -7/9 is not a special value, so I still want to have a visual and say, okay, -7/9, so that's almost all the way to the outside. So I am looking for 2 values, one in quadrant 2 and one in quadrant 3, but I'll have to use my inverse cosine to get me at least one of those values to get started. I'm getting that inverse cosine of -7/9 is roughly 2.46. So that's going to be this top arc right here, about 2.46. And then again for the bottom one, I've got lots of cosines in this set. We could do a -2.46 or a 2 pi minus 2.46. That's probably going to be a good choice for getting a positive answer for this time thing. Okay, so we're going to say that pi over 5 times t minus 4 is plus or minus 2.46. And then we can multiply both sides by 5 over pi. Oh, I'm sorry, I need to write my 2 pi k at the end here. So we will get plus or minus 3.92-ish, and then this is going to be plus a 10k. So we already decided the period needs to be 10. If you want to just remember that and tack it on at the end, that's fine. Just don't forget. I like the algebra to do it for me because I'll find that I forget and write a 2 pi k even though I already knew it should be 10. And then last thing here is we're going to add 4. We're going to have to split that up to make that true. So if we do 4 plus 3.92, we get 7.92. And if we do 4 minus 3.92, we get 0.08. And then those are going to both have a plus 10k. doesn't really need that minus. Not that it matters because k can be negative, but really we just need to write that. So those are my two choices. That minus 3.92 actually worked out really nicely because I think it got me my first, what's the first positive value of time? Yeah, that one actually got me my first positive time. So it's a 0.08. So 7.92 is great, but it's not the first time we hit there. And we should be able to check this graphically as well. So we're looking for when height equals 0. So you can see over here is that 7.92, but there was one just past t equals 0 that we hit. So please check graphically. I think that's really powerful and good, but I still want to see the algebra for something like that so that I know you can do both ways. And then the last question is, at this time, was it going up out of the water or down into the water? So just looking at our graph, I think is the best way to answer that again. If we're looking at the 0.082, then we can see that it is actually going up out of the water at that point. So that should be our answer for that very last question. Okay, let me know if you still have any questions about this one.